Okay, this screencast accompanies the Ealing film loop, the measurement of G, the Cavendish experiment. I show this film loop during lecture. This is just a supplement to those lectures, posting this screencast here for you on YouTube. I also have a raw recording of just the film loop itself here in a playlist on YouTube. Okay, let me go ahead and set this into motion, like so. Okay, now the Cavendish experiment makes use of a torsion pendulum. The torsion pendulum is shown here in this box. They've encased the pendulum here inside of this box, and they've evacuated the air from inside the box. So the pendulum is able to oscillate in the vacuum. Okay, now what they're doing is they're shining a light here onto a mirror that's right here like so. The mirror then reflects the light to this meter stick that is here in the distance. This then shows us the positioning of the pendulum at any moment in time. Okay, now what they have to do is they have to get the initial position of the pendulum first. So the way that they do this is they take these large, dense lead balls, they're very heavy and massive, and they place them diagonally across from the pendulum like so. Okay, so one of the ex-presidents of the United States reaches in, and then he positions like so the two large lead balls diagonally across from each other. And then over the course of several hours, the pendulum oscillates back and forth and eventually lines up then with the balls. This then becomes the initial position of the pendulum. This is actually then when the experiment starts. Okay, so they're going to show us the initial positioning here of the pendulum on the meter stick in the background. That's given like so. Okay, now the actual experiment begins. What they do to begin the experiment is they then rearrange the positioning of the large lead balls. They switch them, if you will. And then what they do is they photograph the approach of the pendulum to its new equilibrium position. They do this at 80 times normal speed. Okay, so reaching in like so, we then reposition the large lead balls. And we do this without disturbing the pendulum, of course, like so. Okay, and now they photograph the approach to the new equilibrium position as the pendulum oscillates. Once again, they photograph this at 80 times normal speed. As it oscillates, the pendulum executes a specific type of motion called damped harmonic motion. Damped harmonic motion was well understood by the time of Cavendish. You could use the details here of this graph, this very characteristic graph of damped harmonic motion, to calculate how much force is being exerted upon the pendulum. And then, with respect to experimental controls, you know what all the relevant masses and distances are. So then therefore, if you use this graph to measure the amount of force exerted upon the pendulum as a function of time here, this will then allow you to measure G, the universal gravitational constant. Okay, what you're looking at here is a kinematics graph. Horizontally, they're showing the amplitude of the oscillation, and then vertically, they're showing time going downwards here on the screen. Notice that the time here is in terms of thousands of seconds. So then therefore, what we're looking at here is several hours of motion for the pendulum to oscillate. So to set up this experiment and execute it, it does take several hours to do. And the reason why the motion of the pendulum here is so slow is because capital G is so small. So what you're looking at here is the position of damped harmonic motion as a function of time. It produces this very characteristic graph. Once again, you can use the details of this graph here to calculate how much force is being exerted upon the pendulum. I do have a raw recording of this film loop posted for you here in its own playlist on YouTube as well. Okay. And then the film finishes up roughly about here. Okay.